Okay, so we did some calculations when we dealt with Henrys and things like that with time constants. We used the values in the book for the first to fifth time constants. They were just basic numbers representing each time constant. So the percentage here, 0.63, 865, 0.95, and so on. So now we'll introduce E, associated with Leonard Euler. I believe it's Euler. 1700s is around the period, I think it was late 1600s, 1700s, somewhere in there. They started making this discovery. It's an irrational number. But when we talk about the exponential curve and things like that, this is really what we can use to calculate it at any point. So, for anybody that's ever watched Arnold Schwarzenegger's Pumping Iron, let's get serious, or real, whichever one floats your boat. So, sometimes this formula can seem a little bit intimidating, but if you just take a second to think about what it is, it's not too big of a deal. We're just using this number here for the calculation. So it's expressed as for a current, so say, start from the beginning here. So T equals L over R. So we've done this and we know that the T is calculating for the first time constant. And T, the symbol tau, so 1.5 seconds. So this symbol, the tau, represents 1.5 seconds, and there's 1.5 seconds in between each one of the time constants. So if we take a circuit, 120 volts divided by 10 ohms, and we'll say we have 12 amps. So we want to know what it takes for this inductor to charge up. So if you, in your calculator, you take E, you go second for the calculator I use, which is the Sharp EL 520XT, or some model like it. If you just hit second function E to the -1, which is also 1 divided by E, you'll find you get 0.367. Now this is where it's important to understand what's going on here. So we have the build-up rate is 0.632. The decay rate is 0.367, which is the inverse of 0.632. At this point, you've built up 63.2%, but this number here is showing you've decreased by 63%. So that's the important part to understand here, that when we get this number, e to the -1, it represents, when you look at your tables for the buildup and decay, this represents the decay rate. So, and that's why right here, because the current is building in the circuit, we apply the decay rate, but we have to have 1 minus this value. And 1 minus this value will give us the 63.2%. So that's where I get little hiccups and misunderstanding as to how we're applying that. So if you wrap your head around that one, you're good to go. And then we have the voltage, because as the current is building, the voltage is decreasing. It's not fighting the voltage anymore. And so as the current is building, the voltage is decreasing. So, and that's why right here, the voltage, we're simply applying E to this ratio here. And because the voltage is decreasing, it's decaying. So we just go with E as it is in this equation here. So this is just a couple different ways to express e to the -1, 2, 3, 4, 5. And when we get into this right here, so -T times R over L. So we have the tau is L over R, which is this right here. So L, if we just invert the formula, is equal to tau times R. So if we plug that in to this formula right here, -T over L, TR over L, negative, so since L is equal to tau times R, we can just change this here. And then the R's will cancel out here. And we end up with negative time over tau. And that's also important where sometimes I get the wrong values being expressed. So it's important to know or to understand that the negative t represents the time and the tau represents the time constant. So what we have here is the ratio of any given point in time to the time constant. So that's the important part there. So if we progress here, what is E? So this is just a basic explanation. You can find all sorts of them. It's used for many, many things. What is E? So with a calculator, enter a 7-digit number, any number. Take the reciprocal of that number, so 1 over whatever number you choose. So then add 1. So here's X, that's the 7-digit number you chose. Here's the reciprocal right here, and then add 1. So 1 plus whatever's going on here. Raised to the power of the 7-digit number. Press the equal sign. So what's happening? Now this explanation 1 to 5, we basically have a power struggle. So 1 plus 1 over n to the power of n. That's what this is here. So if we just take some simple numbers here, and so you got 1 over 2 to the power of 2, 4 to the power of 4, 1 over 8 to the power of 8. And we keep going. What we find is we get closer and closer and closer to this number. If we just keep going, this number will just keep becoming more and more precise as we go. It's been calculated to many decimal places. But that's sort of the idea here. So as n approaches infinity, we're just going to get closer and closer to this number. So that's the base idea, is the idea of the power struggle between the two. And we end up with this number, which is applied in many different ways. So here's one of them. So at the base, as n gets larger, we get closer and closer to 1. So there's a battle to infinity between 1 over n and the power of n. So how can this be applied? Well, if we just take some banking, at $10,000 into savings account at 6% per year. Now this is just to the power here. But the idea of just keep growing. So if we have year 1, $10,000 times 6%, 10,600, year 2, 236, and year 3 to the power of 3, and it keeps going. So if you just think about this here, what if we took this rate and instead of each year, we applied this each month? So you'd find over the years, well, if each month it compounded by 1.0 or by 6%, well, you'd end up at the end of 1 year with a much different number right here. And that's what you're going for. So good luck with that. But that's the basic idea of the exponential values here. So after t years, you got 10,000 times 6% of the t. And hopefully you get to reach an early retirement. So if we take the calculator here and we just take a basic circuit, and we punch this in. So we got a 120 volt circuit, 12 amps. Just a resistive inductive circuit. So we have 12 amps, and punch this into your calculator. So you would have, now we're dealing with the current. So again, the current is building. That's why we have 1 minus E. So if you punch it into your calculator exactly like this, 12 amps, well, 12, open bracket, 1 minus second function E to get the E. It'll come up to the power of, and you open the brackets again, And what it'll look like is this right here. But so open bracket 1 minus, so second function e, negative 1.5 to 1.5 gives us 7.5 amps. So now 1.5 is relative to what we're doing here. So 1.5 seconds was the tau. So that's the 1.5 second increment in between each one. And that's what we're looking at here. So we have, if we just plug this in, so I is equal to E over R. So this is just otherwise known as I max. So this is just a little bit of a breakdown. So we have e to the negative 1. So again, the ratio of 1.5 to 1.5 is 7.58 amps. Now if we just take this calculation to each time constant, so this would be 1.5 is the first time constant. We add another 1.5. This is the second time constant, and we just keep adding 1.5 to the 3, 4, and 5. So, and again, the ratio of the where we are in time, the time constant, to the tau. And that's what's being applied here. So, and that's why we get e to the negative 2. If we have 3 divided by 1.5 equals 2. So we have 12 amps times, so you can punch this in either way, negative 3 over 5, but it will get you 2. So just showing here the very simple values at the exact time constants. Now you'll end up with a little bit different numbers compared to the values that are in the book. It's a little more precise. So 10.3, 11.4, 11.7, and closer to 12. So if we go to the next and we do the same thing, only with the voltage. Now again, the voltage is decaying, so we're not going to use the 1 minus. We're just going to go right from 120, second function E, open bracket. Punch these numbers in, we're looking at 44.1 volts. So as long as all of my math is correct, so we got the first, second, third, fourth, and again the ratio of time constant to the tau, 44, 16.2, 5.9, 2.1, and 0.8. So it's slowly breaking down. So we can calculate this at any point. So if we have a voltage of 120 volts, a current of 10 amps, now we're just breaking free of everything previous here. Now we just have, so we have a tau of 0.5 seconds, which would be now 0.5 seconds in between each time constant. We have, and the time, so we want to calculate for, so we have a tau of 0.5, and the time we want to calculate for that is elapsed here is 0.8 of a second. So slightly past the first time constant. And all we're doing here is, so for the voltage, 120 volts times e to the ratio of the time to the tau, that gives us 24.2 volts. The current, 10 amps, 1 minus ratio, gives us 7.9 amps. So if we just take this next value here, 200 volts, 40 amps, 0.8 seconds for tau, and 1.2 seconds for the time. Pause the video and try to work it out. Here's the answer, 44.6 and 31. And if we progress to one more, 90 volts, 3 amps, pause the video, try to work it out. Tau is 0.15 seconds. 38 seconds is where we're at. Pause now. And the answer, all assuming that what I've done is correct, is 7.1 volts and 2.7 amps. And that is it for E.